Notes today. No staple.
Short and sweet.
Short and sweet. So what I would like to propose, notes first, rest of class problem set. I'm anticipating at least 30 minutes. I would like to start and finish though with this piece of paper. This is not a formal piece of paper, but I want to get some ideas as we start kind of moving through this unit. Very much like the integration techniques, which your tests are almost finished being graded. I woke up at 5:15 to grade them, and it still wasn't enough time. I want to start talking about what methods to choose when. So right now, this is a little more intuitive because we only have really one method right now, which is geometric series. So I'm going to give you this. There are 10 different series. I want you to just think out using whatever knowledge you can. Does it converge or does it diverge? For the geometric ones, if you can find them, you'll be able to give an actual proof. For some other ones, you might have to think about it. If it helps to list out some terms, so you could start by plugging in 1, plugging in 2, plugging in 3, whatever. I want to see how much we can figure out. By the end of today, we should be able to rigorously prove 1, 2, 3, 4, 5, 6, 7, 8, 9 of the 10. So we'll revisit this at the end of class, so don't throw it away immediately. But when you get it, see if you know, does it converge or does it diverge? It does not have to be formal right now. My hope would be that you can identify which ones are geometric at least. Also, it should be said that I don't want you to work on your problem set right now. Otherwise, I will make these notes last forever.
Last time was rough. I had
All right, I'm going to give you about 7 minutes to think.
Okay. Wait, is this the no? This one diverges. Why are we starting? Okay, R for number 1. What am I trying to
Or it's less than 1.
do? And the absolute value of R.
This is greater than 1. That's less than 1.
Greater than 1.
Yeah, but does it read the R number? I think this is plug in. That's
I'm gonna have to go with, I think diverge anyway. We're gonna have to go with, diverge. Why are you sniffing around? Why do you keep sniffing around?
No, wait a
Arithmetic or arithmetic?
And then number 4.
arithmetic. Air. There you go.
Number one.
Oh, well, I love quiz today.
All right, if you think you've written them down, write down some reasons. Write down
Do you want to write like? But you can write it like any.
This is just
It sounds very good. Or give it to your guys.
Three.
I'm gonna say two. So, I think for this one.
What am I doing? That's the funny thing with it. No, wait, wait. I just wrote wrong. Negative one.
Oh, is that what's showing you wrote it down?
No, that's scary. Negative one. Squared.
12 minus 2.
I don't know. Phonics is a lot. His friends will probably be right too.
Alright, does anyone feel confident about any of these? Did you see a geometric one that we can actually prove? What are you thinking? Alright, is that Okay, is this one of our geometric ones? Yeah, this guy's geometric. What's that 3/4 that Michael was talking about? What do we name that? R. So our absolute value of R is 3/4. Why do I care? It's less than 1. So that one we can actually prove with geometric series test. We know about our R. Did anyone else find another geometric one? I would say there's at least 2 other ones here. Number 7. 7's kind of geometric. Number 3 is very geometric. Why?
So it's greater than 1.
Is it?
Yeah.
All right. Yeah. This is pi over e. Pi is 3 something. E is 2 something. So that's greater than or equal to 1. This diverges. There's another one that's very geometric. Did anyone find it? 8? 8's kind of weird. I guess you could count it as geometric. That would work. 4 is definitely geometric. How can I make this look like a geometric function? Okay, so I could do this, like that. All right, so what would the fraction inside be? I know it's 1 on the top. 9, good. Yeah, because I multiply exponents. So here, 2 to the n, and like 1 to the n is just 1. All right. So this one is geometric. What's R? Why do I care? Cool. All right. You're saying 8 we can kind of count as geometric. Did anyone list out some terms for this one? Yeah, so it's alternating, kind of like that, what Austin was noticing last time with, he related it to oscillating. We're going to call it alternating with the terms. Our first term would be -1 because it's 1 to the -1, but then it would be +1, -1, +1, -1. We could, so the problem with this one is depending on the way you group it, you can get different sums. So if I group it this way and add those together, I could get 0. If I group it this way, I could add it together and get -1. If I group it together different ways, I can get different things. So this one actually will diverge. If we call it geometric, we can say this for real. What would the R be? Absolute value of -1. So we'd get 1. Oh, sorry, -1 for the R. Yeah. Yes, and then the absolute value would be 1, which is greater than or equal to 1, so this would diverge technically as well. All right, those were all the ones that I would consider geometric. Did anyone else have strong feelings on any of the other ones? 7 you had strong feelings about? All right, so what do you think this does? All right, we'll be able to prove that one today. Any other ones you thought about? 9? Ooh. Did you list out any terms for this one? Ooh. We're looking at some series right now. I don't know where I put it. I'll find it in a sec. I don't want to give you my filled out list. Where did I put these? Oh, there it is. So you simplified that?
Well,
For number 9, did anyone list out some terms instead of like trying to simplify it?
I figured out that the 1 over n plus 1 is always going to be smaller.
Okay.
So it's always subtracting a smaller number.
Okay, that's fair. So, all right. We'll look at that one later. Yeah. Oh, just made a common denominator, so multiply this one by n plus 1 over n plus 1. And this one by n over n. What do we think this one does? Did anyone have like a gut feeling on what you think this one does? You think it diverges? You think it converges? All right, let's do a vote. Who thinks it converges? Who thinks it diverges? All right, so we're not convinced yet. Was anyone convinced about any other ones? Let's go from the top. Number 9? Number 10? What do you think number 10 did? Why? Why? Explain. Oh, so the groupings I have are -1 plus -1 plus -1. That sounds like it would diverge. All right. Any thoughts on
5 is definitely diverges.
5 is diverges? Converges?
No, it definitely diverges.
James is right, but I talked to him earlier. This is the only one where we will not have an answer at the end of today. So I'm going to tell you this one does diverge, which will be interesting. How? This one is an interesting one. We're going to talk about this, and it's going to be a good counter example to one of the tests we're going to learn today. Did anyone have strong feelings on 1, 6, or 9? 1 diverges? How do you know?
It goes to negative, so -2 times.
Okay, so did you listed out some terms? So maybe -1 is the first term, -3, -5, -7. What was this one called? We had some like this last time. An arithmetic series? Arithmetic. Arithmetic series, all of these are going to diverge. We'll have better language for that today. Did anyone think about number 6? What do you think?
I mean, you couldn't really gauge the plus or minus rate after a certain point in time. You probably fall.
Okay, fair. Does it get small enough? I guess we'll find out. What do we think about number 6? Who thinks it converges? Who thinks it diverges? All right, still half and half. All right, we'll have information for this one today. So what I want to do is we're going to talk about 2 new series tests today. If you could keep that piece of paper kind of on your desk somewhere, we're going to revisit it because the ones that weren't geometric, other than number 5, we will be able to prove with something we learned today. We're going to talk about 2 series tests. Notice our first question is one of the ones we were debating about. So we're going to talk about telescoping series, and we're also going to talk a little bit about sequences of partial sums again. So like listing out the first few additions, and then we're going to talk about something called the nth term test. The nth term, I like to compare it. Remember back when you first learned limits, and we learned about direct substitution, and me or your teacher said, try this first, try this always. That's the nth term test for this unit. So it's going to be something we always check for at the beginning. So going to pass these out. Again, no staples, so we're going to go pretty fast. We'll revisit that does it converge, does it diverge, and then I'll be done talking.
Thank you so much. I'm so done with today's.
Well, can you be done in like 20 minutes? Is your problem set done?
It's like I'm like basically giving up on that. But it's where you gave us the volume and we had to find K. Yeah, okay, Mindy, we'll.
You're crazy.
Okay,
All right, so we're going to use, we're going to do, the front page is going to be all telescoping. The back page is going to be all nth term test. Nth term is super easy, so the front page is really what we're focusing on. Now, I want to reflect back on what we did last class when we started investigating geometric series. Remember when we started listing out these partial sums here by adding up the first few terms? Okay, so that's kind of a good way to get a sense of what's going on. But most of the time, we can't find like an equation for that. We can't find an equation that gives us what would these be if I listed them out. For telescoping series, we're actually going to be able to because some really cool stuff happens. So while this was kind of an investigation, with telescoping series today, we're going to actually be able to find a formula to find a limit of to see if the sums go a specific place. So let's talk about telescoping. I'm not really sure why it has that name. Maybe. I have a projection. Yeah. Think of what that does. Collapses right on in. So we're going to talk just about this series. So a great way to figure out what a series does is to start listing out terms or to start finding some partial sums. For this first one, I'm going to find S sub 1 through S sub 3. I think after that, you're going to be able to give me a formula for the nth partial sum. So we'll talk about what I mean by that. Now, as I find these partial sums, I am not going to simplify them for a very specific reason that you'll see in a second. So my first partial sum is just my first term. I'm going to do 1 over 1, which is 1, minus 1 over 1 plus 1, which is 1/2. I'm not gonna subtract those. I'm just gonna leave it. My S sub 2 is going to be that term plus if I plug in 2. If I plug in 2, I'm going to have 1/2 minus 1 over 2 plus 1, 1/3. Let's pause. Do you notice anything cool? What do you notice? Okay, and one of them's negative, one of them's positive, right? So do these go away? Whoa. All right, let's do S sub 3. I take this one. I take the second one. And I add on if I plug in 3, which is 1/3 minus 1 over 3 plus 1, 1/4. Do you notice anything cool? Okay, so 1/3 is going to go away. Eventually I have the 1/4. Let's find out. So let's see if we can write a formula for the nth partial sum. What is going to be in all of the partial sums, no matter how many terms I list out? 1. Now, I need to find a way. There is some uncanceled stuff at the end, right? If I had to write that in terms of n, meaning I'm going to write something that has n's in it, what could I subtract off to represent the last uncanceled term? 1 over n plus 1. All right, so notice that for the third partial sum, it was 4 at the bottom. Now, this is almost never going to happen. Telescoping are pretty cool in that we can actually find a formula for the partial sums. And all of this verbiage at the top means if I take the limit of this partial sum, I will get the limit of this series. So if I do this, 1 over n plus 1, where is this 1 over n plus 1 approaching as I shove n towards infinity? 1 over infinity plus 1. It's going towards 0. So this whole thing is trending towards 1. So what did I just do? I found a formula that represents every partial sum as I go. As I take n, the number of terms, and shove it towards infinity, I get 1. So what word could I use to describe this number 1? It's short. It has 3 letters. Starts with S. Who plays Wordle? It's the sum. So if I can find the limit of the partial sums and actually get it, I get 1. Since I got 1, what do I know? Does this series converge or diverge? It converges. Now, when we really do telescoping, we're looking for this canceling pattern. So even though this is all cool up here to find the sum, we can say, based on our work with the canceling, that this converges by telescoping series tests. This is one of the few tests that we're going to do where it's kind of just look and you see the behavior instead of like find a number, tell me why I care about the number. All right, should I make this a singular step harder? All right, for this one, instead of writing out S sub 1, S sub 2, S sub 3, I'm just going to start listing as many terms as it takes for me to see the pattern. All right, if I plug in 1, what's the first fraction going to be? All right, what's the second fraction going to be? Cool. All right, let's plug in 2. 1 over, oh no, minus 1 over, oh guys, it doesn't look like the one before. Nothing canceled. All right, what happens if I plug in 3? 1 over 7 minus 1 over 13. Did anything cool happen? All right, wait. What happened? Okay. Is it 13? Oh, it's 11. Sorry. Brandon, I trusted you.
I don't know why you asked.
I even have it done right here. And I was just like, yeah, 13. I know there's odds. I just know there's a lot of odds.
I'm running less than 200, so I don't know why you expect me to do
Oh, okay. All right, so wait. What's the next one? 1 over 9. Oh, here's the 13. You were just early.
Yeah, I was just.
Okay, so now, I can see something happening. I can see, wait, what cancels now? The 9s. All right, do you think things are still going to cancel as we go? All right, so if we wrote one more term, what would cancel next? The 11s probably. Do you think eventually we would cancel the 13s? All right. Now, to be fair, I should write a plus ... at the end because I'm setting this equal to an infinite series. What's going to be left over, though? 1/3 and 1/5. So just for your edification, I can be left over with multiple things. Now, let's try to write a formula for the partial sum. So what did we say was left over from this? 1/3, 1/5. And if we had that kind of last term that was uncanceled, if we were at the nth term, what could we write for that last uncanceled term? Yes, that 1 over 2n plus 5 would be that kind of last uncanceled term. But notice if I take a limit of this again, that part will go to 0, and I'll just get 1/3 plus 1/5. That's the 5. All right, if I simplify that, I'm going to get, I think, 8 over 15. What could I call the number 8 over 15? The sum. That's equal to this series. So if I wanted to say this equals something, it equals 8 over 15. This is times 5, so 5/15, 3/15.
Wow.
Fractions. All right. Is that how you add fractions? Yeah, you find a common denominator. I like that we just talked through an infinite series and everyone's like, yeah! And they're like, how to add fractions? What? All right, so wait. Based on our investigation, converge or diverge? By what test? So when I first learned this, I was like, why the heck would they call it telescoping? Think of, James was making the Seafarer telescope. Think of that thing and you can collapse it. They often call this behavior where all of these terms collapse into one or a couple of terms. I think that's why they name it that, where it's like.
It's because you're looking to the future for the end.
That's fair. You could also think of it there. So I'm not really sure why they call it that. All right. All right. Last thing I want to show you for telescoping is I can have something that appears to be telescoping, but might not be what we want it to be. So let me show you a weird one. Let's start listing out terms. What do you notice about these terms right away that's a little bit different? All right, they're under a square root instead of in a fraction, which is interesting. Okay, the left one is kind of bigger than the right. Yeah, that's right. The left one's bigger than the right one. Sorry, I got my lefts and rights mixed up for a second. All right, so let's list out some terms. Let's see if it collapses like it did before. So if I plug in the first one, what am I going to get? Square root of 2. All right, which I'll write 1. All right, if I plug in 2, square root of 3 minus square root of 2. Did anything cool happen yet?
Oh, yeah.
All right, next one, what would it look like? I'll write root 4, that's fine. Minus square root of 3. All right, does anything cancel? Is anyone getting a little nervous though?
You're getting terrified.
Why?
We're gonna have one left for each other term.
Well, let's find out. Let's keep going. Whenever you think you don't know something, list more terms out. Why not? What did we plug in last? 3. So root 5 minus root 4. So it looks like we're going to cancel something every time. I'm pretty convinced that I'm going to cancel something each time. Does anyone notice something weird about the things that kind of like this thing at the end? I'm asking a really vague question and hoping for a specific. Okay, so I am leaving the front first term instead of the front second term. Anything else you notice that's different than up here? I know that's a very vague question. Okay, let me, oh, what's left is positive. That is different. Is the thing we're leaving, as I go term by term, is it getting bigger or is it getting smaller? So we left, after the first one, we left square root of 3. After the second one, we left square root of 4. Now we're leaving square root of 5. The next one we'll leave is a square root of 6 and square root of 7. That's a little concerning that it's getting bigger, right? Because let's write our S sub n. Let's write our formula for the partial sum. Which one's going to remain uncanceled forever for all time? The -1. But then which one, it looks like it's positive every time. What could I leave as like the uncanceled term? All right, what's going to happen as I take this guy and shove him towards infinity? Yeah, this is going to go towards infinity. If we get infinity as the answer to our limit of our sequence of partial sums, what do you think this series is going to do? Now, we don't really want to say diverges by telescoping series, and you're not going to see very many questions like this. And honestly, these are going to be multiple choice. This is actually based off of multiple choice that I saw on AP Classroom. What I would say for this is that the limit of the partial sums, so that's what we found here. We found a formula for the partial sums. You could say does not exist, or the partial sums grow without bound, anything like that. I just wanted to show you that sometimes things will cancel, but we need specific behavior of the things that are canceling. So that's kind of telescoping series. For the most part, you're going to see ones that are like this, where they're going to cancel, but it does provide a cool opportunity for us to see ones where we can actually write a formula for the partial sums. Now, that is going to happen about 0.1% of the time. Usually, we're going to have to base all of our behavior on, or all of our conclusions, our converge or diverge, on the behavior of what's called the nth term, so the formula inside here. So when we looked at geometric last time, I'm going to kind of scroll through our notes. Why were we convinced that like something like this was better than something like this? Before we talked about the ratio, why were we liking terms that were 3/2, 3/4, 3/8, 3/16, 3/32? Why did we like those as far as converging? They got smaller, and eventually, if I pushed all the way out to infinity, how small would they get? Super tiny. If I could make it to infinity, how small would they be? Their limit would be going towards 0, right? Because eventually, if I want this thing to converge, if I actually imagine reaching 0, I should be adding nothing on here. So what the next test we're gonna do is called the nth term test, specifically for divergence. If you want to make me mad, tell me something converges by the nth term test. That is not true ever. So this is a test specifically to see if something diverges. It is the easiest test in the entire world that we're going to do all year. So if you can use it, you should. So just like direct substitution for limits, you're going to check this first and you're going to check this always. If your nth term does not trend towards 0, your series diverges. End all discussion, doesn't matter. Because if it doesn't go towards 0, you're adding either something positive every time or something negative every time. That's not good. It's going to either shove your series towards positive infinity or negative infinity. So let's see how easy this test is. So we're going to take a limit of the nth term. When I say the nth term, I mean the thing inside the series. 2n plus 3 over 3n minus 5. If you were wondering why we spent so long on limits, here we are. All right. Anyone remember how to evaluate a limit like this? Yes? How do I do it? All right. So we're looking at, in my class, I often call this same powers, different powers. So looking at the ends, do I have the same power or different power, top and bottom? All right, I heard someone saying 2 over 3 because I'm doing the ratio of the coefficients. So like I said, a lot of our series tests are going to give us a number. Our number from this test is 2/3. The next thing I ask myself once I get the number is, why do I care? Why do I care about this number? It's not 0. So that means eventually, if I reach out to infinity, eventually I'm going to be adding 2/3 every time. That's making my sum too big. So this diverges by nth term. That is like the least amount of work that you're going to have for any test that we do this year, minus maybe geometric. So if you can do this, you're going to want to do this. All right, let's look at the next one. Anyone remember factorial? Factorial. Oh, math gets exciting again. All right, so let's, anyone remember how to do like 5 factorial? So you take that number and you multiply down. So you're doing 5 times 4 times 3 times 2 times 1, and then you stop. So factorial doesn't work for negative numbers. It doesn't work for fractions, at least in the context of our class. Anyone know what 0 factorial is? Close. It's 1, and this is literally by definition. They said it was that so that a lot of things in probability work. What? 1 factorial? 1.
When I see things like this, it makes me think that a bunch of people just sat under a tree and made up random rules.
So this one more so, they didn't make it up randomly. They made it up. So a lot of the, like, remember combinations and permutations from Algebra 2? Kind of.
Very big.
So if you remember those words at all, it's like if I have so many things in a bag and I like pick out 2 blue marbles, 5 red marbles, whatever. A lot of those things don't work if you don't have 0 factorial equaling 1. So they did it by definition is why it's true, but by necessity also to make those things work. All right, either way, factorials are gonna come back in a big way. They cancel really cool. So let's take the limit of this nth term. All right, as you might be able to tell, as I shove n towards infinity, factorials are gonna get really big. Because think 10 factorial is 10 times 8 times, I skipped 9. 10 times 9 times 8. I skipped 8. 10 by 8, 7, 6, 5, 4, 3, 2, 1. You're multiplying. So these are going to grow pretty big and pretty fast, but I have an n factorial on top and bottom. So same idea as what we did there, same power. So what do you think the answer to this is going to be? 1/2. Why do I care? Conclusion? By I should probably write test. Yeah, this test is easy.
We have to write tests on it.
I'd probably be fine with end term. All right, this one looks kind of geometric, but that -2 is making me not happy. All right, same power or different power? Does it have the same power vibe? Yeah, it's because those 3's, the bases are the same in this case. So if I had 3 to the n over 2 to the n, the 3 to the n would be winning. But here we go. What do you think this limit is? 1, because you can think of times 1 here, times 1. So the coefficients of those. Why do I care about the number 1? Conclusion? I do like the order of the units because by the time you're sick of something, we're moving on to completely something different. All right, what does this limit equal? Conclusion? No. No. If you have this, you know nothing. Jon Snow. Yes, so thank you for emphasizing my point, James.
You wanted me to say it was 0, right? You wanted me to say convert.
It doesn't matter. All right. So I really want to emphasize this though. So everyone really pay attention for a second. This test is easy. Yes, you're going to want to use this test for everything. You cannot ever use this test to say that something converges. We are going to run into so many series where the terms get smaller and smaller, but they diverge because of other things that happen. This one is going to be so popular, he's going to have his own name. But the vast majority of series, because this series test is so easy, the vast majority of series that we work with, the limit will go to 0. So we're going to need more tools in our tool belt. So if you get 0, nothing. You know nothing. Yes.
So is it kind of like, so if this test fails,
So if this test fails, you're going to have a heck ton of other choices to use. So if it looked like geometric, you could do geometric. There's something called a limit comparison test, ratio test, direct comparison test, root test. What else do we got? Alternating series test. But, I do like what Austin said where he was using this test first. So if we can use this test, this is the one we're going to want to use because it's easy. The other ones that we do are going to be a little bit harder. We're going to have an order of which we're going to try to use them in. There will be a flow chart that I'll give you. It'll be fine.
I like how you take one of these options to solve it.
Yeah.
7 is a rotation, and then unit 8 is
Pick one of these options. Yeah, so it does have that vibe. All right, hello. Yeah, Sydney. Guys, can you listen to this lovely question? What if the powers are different? So let's say we had a limit here. Let's say I add a square down here. I had 2n plus 3 over 3n squared minus 5. Where does this limit go? 0. Converge, diverge, don't know.
We know nothing.
We know nothing. What if I put the squared up here? Converge, diverge, don't know. Is that 0? No. Diverge. I can't, those are the 3 options. Yes. So same power ratio, top heavy, infinity, bottom heavy, 0. All right, and I could do the same thing for something down here, just to be really clear. If I change this base, so like 2 to the n over 3 to the n, this one will go to 0, I know nothing. This infinity diverge. So we'll talk a lot about other ones. I'm going to save that discussion, Sydney, for factorial because factorial interacts with itself a little bit more weirdly. So let's do a little bit of instruction. So that's all the notes for today. Let me give you some stuff. So I need your attention, first of all. I know we're all very excited. But, oh wait, before we problem set. Hello, hi. Can you find this paper again? All right, I'm gonna tell you a bunch of these work with nth term now. Can anyone see one that works for nth term? All right, 6. If we look at this one, the limit as n approaches infinity of this is what? 2/4, which is not 0, so this diverges. All right, the limit of this one is what? 3. Why do I care? What's number 9? What's it called? Telescoping. We could list out some terms to prove to our reader that we know it's telescoping. We could find that thing. Where there's another one that's nth term. Where is he? Oh, we could do the arithmetical with nth term, right? If I took this limit, where would it go? Negative infinity. Why do I care? That ain't 0. All right. Notice for the ones where the geometric has a r less than 1. So like this guy right here, that was 1 over 3 to the 2n. Notice these do converge not because of nth term, but this limit does go to 0. So that's helpful. It confirms some of our thinking. This one, if you took the limit, notice the terms taught back and forth between -1 and 1. So does this limit exist? Yeah, this does not exist because of oscillating behavior. Finally got to use that word appropriately. Oscillating is just a great word. Other math words that are great, orthogonal. Great word. Do you want to know what orthogonal means?
Yes.
All right. Perpendicular lines. This is perpendicular. This line is normal to this curve. Those curves are orthogonal.
So wait, they're perpendicular.
Yeah, their tangent lines are perpendicular. Cool words. All right, so let me just give you a little bit of schedule update. So by the end of class today, what should I have in my hands? Problem set. I do have my, can we just stop talking while I'm talking? All right, thank you. That was a very quick response. All right. I do have my answer key. I'll be sitting, I might just sit at this set of desks. If you want to check anything, if you can respect other people's time and not just like give me your whole problem set and be like, check this. If you could check maybe a couple questions at a time, that'd be totally fine. Let's remember as we work the difference between helping each other and copying off each other's papers. If I see the latter, there's where you're turning your problem set in. I don't go in there after I put things in there. So don't make me do that. What is happening next class? A test. Let's go over the options for that test. Do I get a partner? Do I get to choose my partner? No. I do. Yeah. I'll probably do that, but I'm going to mix them up a little bit. So I try to make sure you're not partnered with someone you could partner with before, just so you can choose some different it's nice to talk to different people. Yeah, Sushan. I'm probably going to do quarter 2 since those are done and finalized. So I'm going to mix them around a little bit, but everyone in this room is good at calculus. So don't worry about it. You'll get a partner who knows what they're doing. And if you don't, okay, if you don't let your partner down. Be good at calculus. Lily, you're not. Last thing as a support for this test, y'all, if you cannot stop while I'm talking, I'm just going to make everyone take their own, and I'm going to make it so hard. It's bugging me. Austin, are you requesting a very hard test? Oh. Sit. All right. Last thing you'll have as a resource. So I'm going to try to make this as mastery as possible, but my little old eyes are going to have a hard time trying to check everyone's work, and I don't want to check someone's and then look at it later and realize I've missed a mistake. So you're going to have a Desmos thing. It's just going to essentially have, like, let's say there's 10 questions like the last test. It'll just have blanks for 1 through 10. I'm going to make sure that if you put in your decimal answer to 3 decimal places, truncated or rounded, it will tell you whether that answer is correct. So let's say the answer is 10.222. That's one of the answers from the problem set if you'd like. If you get that answer, you type it in. There will be a little message that says correct. I may also even try to program in if I see a couple of frequently missed things. If I know there's going to be a common mistake, I might try to put a comment in there that's like, hey, check your subtraction. Actually, I might do that if you get a negative answer. So that will be there. And then I'll be walking around the room to try to answer any questions, give any nudges, or if you're kind of done with all your right answers, if you want me to start checking your notation and things there. My plan, since that support and that partner will be there, the plan right now is to not round to this test. If we are coming into this test and it doesn't go the way I'm thinking it'll go, the reason I'm saying that is I'm confident we're going to do well. If I'm wrong, that's okay. I will make sure we get time to review and do round 2 if we need to. But I think since I'm going to shorten the test, make it sweet, short, to the point, I think it'll be fine. Last comment on the test, remember the focus is on the setup and not the integration. So most, if not all, of the questions will be integrate on the calculator, not integrate by hand. So if you're focusing your studying, I would focus on the setup and not can I integrate and actually solve for an answer. I'm going to get a review posted. If you don't see it soon, please, please, please just email me to remind me. I have a lot of things on my to-do list, and that is one of them. It's not the top one. So just remind me. All right, you guys have the rest of class. It's about 33 minutes to get that problem set done. I'll be sitting with my answer key over here. If you have any questions, go. Okay, I only have, I think it's one question. Let me stop this recording. Yeah.